Hi everyone. In our most recent class, we focused on statements involving rational and irrational numbers. If the statement was true, you were asked to prove it was true. If the statement was false, you were asked to come up with a counterexample. Here's an example. The statement is, the product of a rational number and an irrational number is irrational. I think it's helpful to take that statement and translate it into a mathematical language. What we're really saying there is for all real numbers m and n, if m is rational and n is irrational, then the product m times n is irrational. If we think that statement is true, we're to prove it. If we think it's false, we're to come up with a counterexample. And remember that a counterexample is an example that shows that the negation of the statement is true. The negation of that statement is there exists real numbers m and n such that m is rational and n is irrational and m times n is rational. It turns out the negation of the statement is true. And here's an example. Okay, so for this, let's let m equal 0 and n equal anything that's irrational, square root of 2. M is a rational number because m equals 0 over 1. In other words, you can express 0 as a ratio of integers where the bottom is non-zero. So m is irrational. We showed that n, the square root of any number other than perfect squares, is irrational. Okay, so m is rational, n is irrational. But now let's look at the product. M times n equals 0 times the square root of 2, which equals 0, which is rational. So we have a case. So m is rational. Remember the symbol for rational is Q for quotient. And n is irrational. And we made up our own symbol for irrational. We'll say I for irrational. It's actually R/Q. The real numbers take away the rational numbers. And m times n is rational. So we found numbers, real numbers m and n, such that m is rational, n is irrational, mn is rational. So the original statement is false. Okay, now there's something about this statement. It says, well, 0 is the counterexample. What if we take 0 away? So I'd like to consider this next statement. The next statement says that the product of a non-zero, so let's take 0 out of the equation here. The product of a non-zero rational number and an irrational number is irrational. So it's very similar to the statement we just proved was false. Only now we've added that condition. The rational cannot be 0. If we think this statement is, again, if we think it's true, then again, it's helpful to translate it into mathematical language. We're really saying that for all numbers m and n, if m is rational and n is irrational, and m is non-zero, so and m does not equal 0, then the product, m times n, is irrational. So that's an alternative version of the statement. It turns out that this statement is true. Okay, when you take out 0, all of a sudden it becomes a true statement. Now, I'm looking at the statement, and there's something in here I don't really like. I don't like this part of it, basically showing that the product is irrational. It's really hard to show that something is irrational. It's easy to show it's rational because you want to show it's a ratio of integers. It's hard to show something's irrational. So that leads me to think of a proof by contradiction. For proof by contradiction, let's assume the negation of the statement is true. Let's assume that, as I state here, that there exist real numbers m and n, such that m is rational, and n is irrational, and m does not equal 0, and, okay, instead of mn is irrational, we're going to assume mn is rational. Where does that lead us? Well, I've started us out on the next page. We said, well, since m is rational, we know that m is a ratio of integers. It's p over q, where p and q are integers, and q does not equal 0. Since m does not equal 0, we can say something about p. If m does not equal 0, then p does not equal 0. Because if it did, if p equaled 0, then m would be 0 over some non-zero integer, then m would be 0. But we said m cannot be 0. So since m is non-zero, we know that p is non-zero. Lastly, we've assumed that mn is rational. That says that mn equals s over t, where s and t are integers and t does not equal 0. Okay, so let's put this together and see what we can do. Again, I'll do it in blue. We know that mn equals s over t, but we know that m is p over q. So I'm going to substitute the first equation into that equation. So what I have is p over q times n equals s over t. Okay, so if that's true, well, I can find n. I can multiply by the inverse of each side, multiply each side of this equation by q over p, and by q over p. Okay, and what I would have is that n equals s over t times q over p. Now I'll put that together. That is s times q over t times p. Okay, so let's see what that gives us. We know that from here, we know, well, that's an awful bracket, but it's supposed to be a bracket. We know that sq is an integer. Okay, and that's because we know that s is an integer and q is an integer. We also know that t times p is an integer. And we know that because we know that t is an integer and we know that p is an integer. Lastly, what else do we know? Well, we know that t does not equal 0, and we know that p does not equal 0, which we said up here. Okay, so we said because m is non-zero, no, p is non-zero. There we go. So we know that t times p does not equal 0, and that's because t does not equal 0 and p does not equal 0. And that's by, again, that's by the zero product rule. So what do we have? So what we have is that n equals, okay, SQ, we'll call that thing, well, we'll run out of letters, we'll call that thing A1 is an integer. And we got that TP, we'll call that thing A2. So n equals A1 over A2, where A1 is an integer, A2 is an integer, and A2 does not equal 0. So let's see, what does that get us? So that says, so if n can be expressed as a ratio of integers where the bottom is non-zero, that says that n is rational. But now I want you to look back at that statement. The statement says, let's assume that there exist integers m and n such that, let me go back to my pen, such that m is rational, n is irrational, and mn is rational. But what we showed through those assumptions, we showed that m is rational. So m cannot be both rational and irrational. So there's our contradiction. So this, okay, so n is rational, which contradicts. Which contradicts that n is irrational. So, since our assumption about the negation, since we assumed the negation was true, that led to a contradiction. So, our original statement must be true. A little box just to show that we finished the proof.